Hello. So I'm going to start with a question which is you might consider a bit of a dud, which is, which pentominoes are convex? And, well, it's that one. So a reminder of what it means for something to be convex is if you take any 2 points in it and make a line from one point to the other, that all the points in that line segment will be inside that shape. So even though that starts out looking like a bit of a dud, you might think about it a little bit more and think, well, are they all really the same in terms of how convex they feel? Like that P pentomino seems more blobby than some of the other ones, and the X is a bit crinkly, and the U and the V seem to have two separate sections that can't really see each other, so that if you try to put points in either section, they'll be forced to go outside the shape. So that seems like a little bit less convex than some of the other ones that are there. And so what we really want then is a measure that we can say that something is convex. It'll be like that I pentomino. It will have a convexity of 1, and if it's really concave, like the 2nd Congressional District of Texas, it'll have a convexity near 0. And that's actually an application of convexity that is a little bit less interesting than pentominoes is gerrymandering districts. But so what sort of measures would we have? Well, one thing we can do is just randomly pick a whole bunch of pairs of points and draw segments between them, and just do that for a very long time until we have an estimate of how convex this thing is. So I've done that with the F pentomino here with completely fake data, and gotten an estimate of 0.8 there. Of course, you can actually do math that gives you a precise answer of how probable it is for one of these chords to be inside the pentomino, but doing simulations is easier. Next thing, and so there's more ways. Another thing you might want is some way of taking your shape that you want to get your convexity for and transforming that into something that is convex. Because if you can do that and it gives you the original shape when it's convex, then that will tell you that you have a convexity of 1. And if it gives you a shape that's different, you can measure that difference between that transformed shape and your original shape. And what we have for this is called the convex hull. You make a rubber band around your shape, and that is a convex shape that's formed from it. And we can make a couple of different convexity measures using this. Oh dear, so our convex hull is a little bit angry. So one thing you can do is make a ratio of the areas. So the area of the shape over the area of the hull. So if something that is particularly non-convex will have a big hull for a really small area. And let's do that for that F pentomino here. You can see the area of the pentomino itself is 5, as one would expect. And with the extra triangles that you can stick those on, and the convex hull has an area of 7, so that gives us that result. Another thing you can do is use perimeters instead. So measure the perimeter of the hull over the perimeter of the shape, since the hull is basically cutting corners and using the triangle inequality to get places faster. You would expect that non-convex things that are particularly non-convex would have a low ratio there. Let's do this for the F pentomino. You see that we get our numbers from the Pythagorean formula over there. And so finally, let's sum up. So which pentomino is the least convex? And the answer is, it depends. If you use that first measure, you say that the U pentomino is the least convex. If it's the convex hull area ratio, you get that set of different pentominoes that are all the same. And by the convex hull perimeter method, you get that X pentomino. And there could be other methods that you come up with, and they will give you different things. So, lessons learned. If you're given something that can be just an on or off values, look for a real valued measure or a spectrum, and it might be more interesting. And second lesson, don't stop there. There could be more than one spectrum. You could do more things. Third lesson, always explore new ideas with pentominoes. It's a great laboratory for everything. Thank you. And Paul thanks you.